if there is perfect positive correlation autocorrelation between Et and Et minus 1, which will mean that phi takes the value 1, right? What will be the value of the Durbin-Watson statistic? 0. So if there is first order perfect, if the Durbin-Watson statistic comes out to be 0, it means that there is perfect first order autocorrelation in the data, right?
Yes.
And what if the Durbin-Watson statistic takes the value, so for example, if Et and Et minus 1 perfectly negatively correlated, then what value will phi take? Phi will take the value minus 1. So Durbin-Watson will take the value 1 minus minus 1 is 2, so 2 into 2, 4. So Durbin-Watson will take the values 4. So Durbin-Watson then can take values between 0 and 4, right? 0 and 4. So if you, is this clear? Is everybody gets this? Right. So the Durbin-Watson statistic will be, if you so if I put this, if I write this axis like this, right? Okay. And if I write the value of the Durbin-Watson here, if this is 2, this is 0, and this is 4, right? A Durbin-Watson of 2 indicates no autocorrelation. So this indicates phi equal to 0. A Durbin-Watson of 1 would be what? So Durbin-Watson of, a phi equal to 1 would be what? Durbin-Watson of 0. Right? Perfect autocorrelation. So phi equals 1 on this axis. And here, phi equals minus 1. Right? So the idea is you must calculate the Durbin-Watson statistic and see what its value is. Now the problem is,
what do you call it when phi is equal to minus 1?
phi is perfectly negative autocorrelation between Et and Et minus 1. You get perfect negative autocorrelation. Right? So large Et today will be a perfectly low negative Et in the next week. Right? Everybody gets this? Now the problem here is, if you get a value, suppose you do this. So what do? You regress Yt on Xt, get E hat t. Right? Then form the sum 2 into 1 minus rho hat. Right? 2 into 1 minus rho hat. That is, form the sum 2, that you find E hat t, you find E hat t minus 1, calculate E hat t into E hat t minus 1, divide by E hat t minus 1 square, and do all the things that are required for this. And suppose you find a Durbin-Watson of 2. Then what do you conclude? There is no autocorrelation in the data. If you get a Durbin-Watson of 0, you conclude that there is positive, perfect positive autocorrelation in the data. If you find a Durbin-Watson of 4, you conclude that there is a perfect negative autocorrelation in the data. Right? Okay? But suppose you find a Durbin-Watson of say 1. What does it mean? It is neither here nor there. Right? So for, especially if you find a Durbin-Watson of 3 for example, it's really neither here nor there. So what will happen is, around 2 for some values, you can be perfectly sure that there is no autocorrelation. As the values, for some values around 0, you can be perfectly sure that there is perfect positive autocorrelation. Right? But for some values, you will be neither sure that there is, whether these values are really close to 2 or close to 0. So there will be a zone of indifference in the middle. There will be a zone of indifference in the middle here. Right? And there will be similar zone of indifference here. Right? So if the Durbin-Watson lies in the, and that zone of indifference will depend upon the number of observations you have, the number of parameters you have in the regression model, and so on and so forth. Right? Okay, so if the Durbin-Watson lies in that zone of indifference, you really cannot conclude whether there is first order autocorrelation or what. But if the Durbin-Watson statistic lies below that zone of indifference here, we'll call it say the lower limit of the Durbin-Watson, and we'll call this say some upper limit of the Durbin-Watson. If it lies between 0 and the upper lower limit, okay, lower limit, then you can conclude that there is first order autocorrelation, positive. If it lies between du and 4, you can calculate the first order negative autocorrelation. If it lies around 2, you will say that there is no autocorrelation. But then there will be some regions where you will be inconclusive. You will be inconclusive. Okay? So that is called the Durbin-Watson test. Okay, the test of first order autocorrelation in the error terms. If you find there is first order autocorrelation, then what you do? Then you use that FGLS, you estimate phi hat, you already have the estimate of phi hat here. So because otherwise you will not be able to calculate the Durbin-Watson statistic, then with that estimate of phi hat, you calculate yt minus phi hat yt minus 1, xt minus phi hat xt minus 1, use yt minus phi hat yt minus 1 as instead of yt, use xt minus phi hat xt minus 1 instead of xt, calculate beta hat and calculate the standard errors accordingly. So basically that new formulation will help you calculate the correct standard errors in your data. Right? Is this clear? Okay. Now this seems a good test, but there are many limitations of this test. One of the assumptions of this test is suppose this is a regression model you are running. Then, and if you are using a Durbin-Watson test, then the assumption for this test is that this is indeed the correct model for the conditional mean of y. This indeed is the correct model for the conditional mean of y. If that assumption is not true, if you do not know what is the correct mean model for the conditional mean of yt, you are basing that the conditional mean of yt would depend upon x1t and x2t. But suppose for some reason you don't know and you are really discovering that from the data, then the power of the Durbin-Watson test is low. Right? Then there is a problem with the Durbin-Watson test. It doesn't perform as well as it does when you know the correct form of the conditional mean of y. Right? The other problem is what you see today is just one form of autocorrelation. Right? There will be other forms of autocorrelation. Right? For example, you could have ET is equal to, say, this is the first order autocorrelation. It could be something like phi ET minus 1 plus gamma VT minus 1 plus V. So the error term ET depends upon its own past value, the value of the past shock to the error term, and a current shock to the error term. Suppose that's the case. In which case the Durbin-Watson statistic doesn't perform very well. The Durbin-Watson statistic doesn't perform, the Durbin-Watson test doesn't perform as well as it should. Okay? But it's a historically very, very famous test of first order autocorrelation, and typically first order autocorrelation is a very common type of autocorrelation in time series data, and therefore it's a very commonly used kind of a test which all of you should know. Right? That's why we spent time developing it. But the general forms of tests on autocorrelation, you'll be able to know if you understand a little bit of more of the time series type of models. Okay? So that's the Durbin-Watson test.